Welcome to Naradar Academy. In this video, we are going to discuss about topology. So this video is going to cover topology, discrete topology, indiscrete topology, order topology, standard topology, and what do you mean by basis, subbasis. Okay, so these are the things we are going to discuss in this video. Let's start with the definition of a topology. See, for defining topology, we take a set X and a collection of its subsets. The collection of subsets is represented by 2. Okay, so X is the set and it will be having subsets. No, the collection of the subsets is taken to be 2, and this is said to be a topology on X if these three conditions are satisfied. The first one is the empty set and the full set X. Both of them should be in the collection tau. And second one is the union of any subcollection of elements of tau is in tau. That is arbitrary union. Okay, arbitrary union of, if you take any union of elements of tau, that should also be there in tau itself. Next one, third one is the intersection of any finite subcollection should be in tau. So what are the three things? First one, the empty set and the full set, that must be in tau. Second one, arbitrary union of elements of tau should be in tau. And then finite intersection. Union is arbitrary and intersection is what? Finite intersection. So if these three conditions are satisfied, then X is said to be a topological spaces with respect to this collection, and it is denoted by X comma tau. Okay, so in a set, in a single set X, we may define so many different topologies. Okay, this topology is not unique in a set. We can define topologies in different ways, right? Okay, if X comma tau is a topological space, then a subset U of X is an open set if U belongs to tau. See, in real analysis, we define open sets in a different way. In real analysis, how do we define? That is, a set is said to be open if it contains neighborhood of each of its points. That's the definition in real analysis. But here in topology, a set is said to be open. A subset of U of X is said to be open if it just belongs to 2. Okay, if that subset is in tau, it is said to be what? Open. Otherwise, it is not open. So, from the definition, what do we conclude? Phi is an open set, X is an open set. Okay, and then arbitrary union of open sets is open, and the finite intersection of open sets is open. Okay, so that is what we have stated. So, just if the set belongs to tau, it is said to be open. Okay, right. Now, let's see some example. If my X is equal to the 3 points at A, B, C, then tau equal to X comma phi. This is a collection of subsets, no? So this contains only X and phi. And this is a topology, and this is called indiscrete topology. We say trivial subsets, no? These are the trivial subsets, no? The collection of trivial subsets that constitute a topology, and that is called what? Indiscrete topology. The names are important. We'll be using the discrete, indiscrete, the words throughout topology. So the indiscrete topology means what? It is the topology containing the full set and the empty set. Okay, let us check whether it's a topology or not. For being topology, what is the first condition to be satisfied? Empty set and the full set should be there. Yes, they are present. Second one, what is the second one? Arbitrary union of any collection of tau should be there. If you take union of these two sets, only two sets are there. If you take union of these two sets, it will be X again. Yes, it is there. And then intersection, finite intersection. You take intersection of these two elements. Intersection of these two elements is equal to empty set only. It is there. Okay. So all the three conditions are satisfied. So this is a topology, and this is called what? Indiscrete topology. So if any set X is given, the collection containing X and phi, that is called what? Indiscrete topology. Then the next one is the same set I have taken. This is one way of defining topology. Another way of defining the topology on the same set. See, I am taking the power set, rho of X. Power set means what? Collection of all subsets. This is a set containing 3 elements, no? So, in its power set, it will be having 2 power 3. That is, 8 elements will be there. That is, X, phi, singleton set, A, B, C, and then sets containing 2 elements, A, B, A, C, B, C. So, this is a power set of the given set, and this is called discrete topology. Okay, I am going to prove this is a topology. You see, first condition, both X and phi are there. Yes. Second one, arbitrary union. If you take any union, that will be again come around this ABC only. Arbitrary union and finite intersection are all there. Therefore, this is a topology, and this is called what? Discrete topology. So, if a set is given, two things are clear. One is discrete topology, another one is what? Indiscrete topology. Discrete means collection of all subsets. Indiscrete means only the whole set and the empty set. Okay. Then next one, the same set A, B, C I have taken. Let tau equal to collection of X, B, empty set. See, first condition is satisfied. X and phi are there. Okay. And second condition, union. If you take union, yes, it will be there only. And then intersection. You take intersection of X with a singleton B. What is intersection of X with singleton B? It is singleton B only. Yes, it is there. And then union, intersection, everything is there. Therefore, what do we say? Again, it is a topological space. So, on the same set X, I have defined third topology. And then one more set we see. X equal to ABC and tau equal to X phi singleton A singleton B. See, first condition X and phi are there. Yes, first condition is satisfied. Second condition is what? Union. You take union of these two open sets. Union of A comma B is equal to the set containing AB, but it is not there in tau. No, so union of these two elements is not there in tau. Therefore, this is not a topology. Okay, next one. The same set ABC, and let me take X phi AB BC. Now here first condition is satisfied. Both X and phi are there. Now next one. What is the union of these two sets? Union of these two sets is again what? A, B, C, that is equal to X. Yes, it is there. But what about the intersection of these two sets? These two sets have B as the common element and the singleton B is not present here. Therefore, it is not a topology. Okay. B is present inside this set, but that is not required. The intersection is singleton B. That singleton B is not present. Therefore, what do we say? This is not a topology. Okay. Then, so we have seen with the same ABC, we have seen 5 different ways of defining a topology. Now, let's see another example. Finite complement topology. Let X be any set and tau of B, collection of all subsets of X such that X minus U is either finite or all of X. See, finite complement means complement of the set is finite. Okay, that is you take any subset of the set X and you take its complement, it should be finite. Okay, that collection is said to be tau f. X minus U is either finite or all of X. Let us see whether it is a topology or not. See, X minus X is equal to empty set, no? This is finite. Therefore, X belong to tau. Okay, that is if X belong to tau means what? Its complement should be finite. What is complement of X? Empty set. Yes, it belong to there. And then now X minus phi equal to X full of X. Either finite or full of X. Yes. So, empty set also belong to tau. So, both the conditions are satisfied. Next, for union, consider U alpha belong to tau f. U alpha belong to tau f means complement of U alpha is either finite or all of X. Okay, that is X minus union of U alpha is equal to, this can be written as intersection X minus U alpha. We know each individual set is either full of X or finite. So, if all are finite, okay, then their intersection is also finite. If all of them are X, then their intersection is also what? All of X. If some of them are finite and some of them are X, then if you take the intersection, it will be only finite only. Therefore, this arbitrary union is also there in the topology. Okay, next one for intersection. Let us take finite number of open sets U1, U2, etc. Un. They belong to tau f means what? Their complement is either finite or all of X. Okay, so if you take the intersection of what? Intersection of ui if you take, what will you get? See, X minus intersection ui is equal to union of X minus ui, but each one is either finite or all of X. So, if you take the union, it will be either finite or all of X. Therefore, again the intersection belong to tau f. Therefore, tau f is a topological space. So, this is called what? Finite complement topology. Okay, or otherwise we call it as co-finite topology. Next one is co-countable topology. Similar to the previous one, if X is any set, the co-countable topology is defined to be collection of all subsets of X such that X minus U is either countable. There we have taken finite, no? Here it is countable or all of X. In the similar way as before the previous problem, we can prove this one also. Now here comes the comparison of two topologies on a given set X. See, let tau and tau dash be two different topologies defined on a set X. Then tau dash is finer. We say subset, superset, no, that concept only here we are using. See, tau dash is finer than tau if tau dash properly contains tau. That is, tau dash is a superset of tau. If you are comparing elements, we say it as superset. Here we are comparing collection of sets, no, so we say use the word finer. Finer set is bigger than the coarser set. This is said to be finer and this is said to be what? Coarser. Okay. Right. Now you consider these two topologies. X is equal to ABC is a given set and tau equal to, all these examples we have discussed earlier. These two are different topologies. You see, all the open sets of tau dash are there in, see, x is there, phi is there, a is singleton, a is there, singleton, ab is also there. Therefore, all the open sets of tau dash are also in tau. Therefore, tau dash, here what we say, tau is finer than tau dash. Okay. This need not be possible always. That is, any two topologies need not be comparable always. They may be, sometimes they may be comparable, sometimes they may be not comparable also. Okay. Now, then the next one is basis for a topology. This is an important concept. Very frequently we will be using the basis for defining a topology. See, we know what is a topology defined on a set. For that topology we define basis. Okay, in vector spaces, you know basis, no? Basis means what in vector space? How do you define basis? It is a collection of elements whose linear combination will generate the entire set. Isn't it? It is the definition of basis in vector spaces. The same kind of concept only we are going to use here. Basis in topology. Here also, basis for a topology is again a collection of subsets of X. Okay, topology is also collection of subsets and basis is also a collection of subsets. Such that, what is the difference? For every element of X, there exists a basis element B containing X. That is, for each element of X, for each element you can find out a basis element containing that element. And then suppose if an element X belong to intersection of two bases, B1 intersection B2, we can find one more basis element B3 such that X belong to B3 contained in B1 intersection B2. Then if these two conditions are satisfied, that is said to be a basis for the given topology. Okay, if you take union of all elements of the basis, that will be equal to the entire set. See, if script B is a basis for a topology, then the topology tau generated by B is defined as follows. So here we have stated what are the conditions for a collection to be a basis. Now here we are characterizing how we say basis generates the topology. A subset U of X is said to be open in X if for each X in U there is a basis element X belong to B contained in U. Okay, so this is how we say the topology is generated by that basis or not. Okay, that means what? For every open set, you have to find a basis element such that every element of X belong to be contained in U. Okay, now for any set X, the collection of all one-point subsets is a basis for discrete topology. We know what is a discrete topology. No, discrete topology means what? Collection of all subsets of the given set. So it is for that set, one-point sets form a basis. Okay, collection of one-point sets form a basis. Next one, let B and B dash be basis for two topologies tau and tau dash. Now we compare that finer coarser concept with the help of basis. Okay, how to compare two topologies with the help of basis. See, B and B dash are the basis for the topologies tau and tau dash. Then tau dash is finer than tau means in case of basis, how will you say? For each element X belong to X and for each basis element B contained in capital B, there exists X. Containing X, there exists a base element B dash such that X belong to B dash contained in tau. See, in basis it will be reverse. See, tau dash is bigger than tau, but here if you come to basis it will be reversed. B dash is contained in B. That is, X belong to B dash contained in B. Okay, next one, one similar concept is another one is subbasis. A subbasis S for a topology is a collection of again subsets of X whose union is equal to X. The topology generated by subbasis is defined to be the collection of all union of finite intersection of elements of tau. So, now first we have defined what's the topology and then we have defined what's the basis for the topology and now we have defined subbasis. Subbasis concept we use very rarely, but we use the concept basis very frequently for defining the topologies. Okay, now let's come to some important topologies. First one is standard topology on the real line R. See, let script be equal to set of all open interval AB in the real line. Then this will generate a topology, no, and that topology is called what? Standard topology in the real line. This standard topology only I am going to make use in this video very frequently. Next one is lower limit topology. Here, if it is the topology generated by open interval, it is called standard topology. If it is a topology generated by half open interval, that is this side, left side closed, right side open, this is called half open interval. No, this topology is called what? Lower limit topology. Okay, and this is denoted by RL. Now I am going to compare these two. On the real line, I have defined two topologies. No, one is what? Standard topology, another one is lower limit topology. I am going to compare them. See, lower limit topology is strictly finer than the standard topology. Okay, so what do you mean? This is bigger than the standard topology. See, for that, now you take x belong to a real number and AB be the basis element belong to B. Okay, then x belong to AB implies this half closed interval x comma B is contained in AB. Therefore, what do we say? The lower limit topology is strictly finer than. But the reverse way is not possible. For x belong to R and x belong to B, there is a base element B dash contained in B. Okay, if in the reverse way, see half closed interval x comma b, we cannot find any basis element a comma b which is contained in like this. Therefore, strictly finer. Okay, next one, the order topology. So far two topologies we have seen. What is that? One is standard topology, that is generated by open interval. Another one is lower limit topology, generated by half open interval. Next one is order topology. For defining order topology, you take any simply ordered set, that is ordered set which is defined with the simple order relation. Okay, then script B be the collection of all collection of all sets of the form all open intervals. Suppose if the set has a lower element, that is infimum smallest element, then it should contain half closed interval, and then if it contains the supremum, contain that is right side closed interval. So the topology generated by all these three kinds of intervals is said to be what? Order topology. Okay, so the order topology is generated by three types of intervals. One is open interval, another one is half closed at left, another one is half closed at right. Okay, if the elements exist, these two will come, otherwise only the first one will come. So this is called what? Order topology. See, if you take the real line, there is no least element and there is no greatest element. So the standard topology is nothing but the order topology. Okay, in z plus means what? Integer, positive integers. In positive integers, order topology is nothing but our discrete topology. Discrete topology means what? Collection of all subsets. Because if you take open interval n minus 1 to n plus 1, it is equal to singleton set n. And if you take this 1 comma 2, because it is only the positive integers, no, so it contains the least element as 1. So 1 comma 2 is equal to 1, singleton 1. So the basis elements are nothing but the singleton set, that will generate the discrete topology. So for order topology, in real line it is nothing but our standard topology. In z plus positive integers, it is nothing but what? Discrete topology. Next one, subbasis for order topology. So we have defined what is the basis for order topology. Now I am going to define what is the subbasis. Okay, subbasis is nothing but contains the open rays a to infinity, minus infinity to a to infinity. Okay, these open rays form a subbasis for order topology. The next one is product topology on x cross y. So far we have seen only on a single line. No, now we are going to see about planes. So let x and y be two topological spaces. Then the product topology x cross y is the set having the basis as the collection script B of the form u cross v, where u is open in x and v is open in y. So script B is not a topology on x cross y, it is just a basis. The topology generated by script B, what is the script B? Collection of all u cross v, where u is open in x and v is open in y. This is called what? Product space. If script B is a basis for topology on x and script C is a basis for topology on y, then D equal to B cross C is a basis for topology on x cross y. The same thing I have stated again. In R cross R, standard topology is the product of order topology with itself. R cross R means what? Standard topology is nothing but order top. In R cross R, we have proved no, order topology, standard topology both are equal only. Now next one is projection. Pi 1 is a projection from x cross y to x and pi 2 is a projection from x cross y to y. How do we define? Pi 1 of xy is equal to x and pi 2 of xy is equal to y. These are called projections of first and second factors. And for this projection, the collection S equal to pi 1 inverse of u, where u is open in x, union pi 2 inverse of v, v is open in y. It forms a subbasis for the product topology on x cross y. Okay. Now let's just visualize how to write this pi 1 and pi 2. See, pi 1 is from x cross y to x, no, and it is defined by pi 1 of x comma y equal to x. See, this is my x cross y. All these elements here are a1, a2, here are b1, b2. See, pi 1 of a1 comma y equal to a1. All the elements along this vertical line will be mapped to the point, single point a1. That is, this line is there, no, that all the points of this line are mapped to single point a1. And similarly for pi 2 of x comma b1 equal to b1, that is all the points in this line are mapped to the single point B1. Okay, so these are called the projection mappings. Next, with one more topic, let me conclude this video. How do we define continuous functions in topological spaces? See, x tau and y tau be two topological spaces. A function from x to y is said to be continuous with respect to these topologies if and only if you take a open set in tau dash, its inverse image should be open in tau. Okay, this is the way we define continuous functions. What should you take? If you take one open set in the range, that's inverse image should be open in the domain. This is called continuous function in topological spaces. Okay. Now x tau be discrete topology, y tau be any other topology. Then every function f from x to y is always continuous, because whatever set you take here in y, its inverse image will be what? Singleton set, and that is always open in discrete topology, no? Okay, so therefore for x being discrete and y being any topological spaces, f from x to y is always continuous. Then next one is constant function. X tau, y tau be topological spaces. F from x to y defined by f of x is equal to p, where p is a fixed constant. Then it is a continuous function, because f inverse of h is equal to the whole of x if p belong to h. Otherwise, it is equal to empty set. Therefore, this is also a continuous function. Then next one is, a function f from x to y is continuous if and only if f inverse of b is open for every basis element. The definition is for any open set. Here, for the basis element also, if you take any basis element of y, its inverse image should be open in x. Next one, for the subbasis element also, if and only if f inverse of s is open for every subbasis element. Similarly, closed set also. What do you mean by closed set? A set is said to be closed if its complement is open. So if you take any closed sets, its inverse images should also be what? Closed. Next one, the projection mappings we have seen before, no? They are, both of them are continuous on which topology? Standard topologies. Okay. Now, two topological spaces are said to be homeomorphic or topologically equivalent if there exists a bijective function which is such that both f and f inverse are continuous. So, homeomorphism means what? F should be bijective, and then both f inverse are continuous. Okay, that's all. Thank you.